Okay, this is David Zierler, Director of the Caltech Heritage Project. It is Monday, April 18th, 2022. I'm delighted to be here with Professor Carol Stein. Carol, great to be with you. Thank you for joining me today.
Thank you for inviting me.
Carol, to start, would you please tell me your title and institutional affiliation?
I'm a professor in the Department of Earth and Environmental Sciences at the University of Illinois at Chicago.
Carol, what is the best term to describe your field of research? There's seismology, there's plate tectonics, there's geophysics. Is there one that works better than the others?
I don't know. I guess I would probably choose plate tectonics slightly over geophysics, but that general area.
And what do you consider a subset of what? In other words, what is the umbrella discipline, and then what are the levels of specificity under that as they relate to what you work on?
I think plate tectonics would be the top one because there's so many different techniques that you can use to work on plate tectonics.
And are you more on the theoretical or the observational side?
More the observational.
And let's go to the theory now. Are there any theories in particular that are important for your work that provide guidance for data collection and analysis?
That's an interesting question. Never thought of that. I don't really think so. I mean, to me, this is not obviously what you're looking for, but I sort of think, is there something that we don't understand or understand well? And then my first approach is usually to go out and get a whole bunch of data and try to understand what the data is telling us.
Carol, what are the instruments that you use that are important for capturing this data?
In kind of the first half of the career, I was looking at how the oceanic lithosphere thermally evolves as it first is formed at mid-ocean ridges and then moves away as it ages and cools. And so I was mainly looking at oceanic seafloor heat flow. Now, I think it's most of the data that I've been using to try to understand continental rifting and passive margins that have formed after the continent rifts and successfully start seafloor spreading has probably been a combination of seismic reflection data and lesser extent gravity and magnetics.
And for you, when is it important to do field research, to go out there and see for yourself? And where is remote data collection perfectly sufficient for the kind of questions you're after?
At some level, it's more if I have an interesting problem and I can convince the National Science Foundation to fund me to collect new data, then I go out and collect new data. Most of the time, it's looking at pre-existing data.
So the default for you is you want to get out there if you can find the funds to do it.
Yeah, unfortunately for the kind of problems that I'm interested in, you can't just kind of pick up and do it on a shoestring. So
I wonder if you can explain, what is the value exactly of being there present on hand?
If you can be there, then you can design your own experiment to gather data to fill in the gaps, to take the data in the areas that you think are critical for understanding your feature, whatever it is. And certainly if it's on land and you can get there and see what's going on, then even if you can't do experiments or make new measurements, you have a better feel for the feature and what some of the issues are and problems and why they're having problems trying to interpret certain features. But otherwise, there's been a lot of data collected over the years and a lot of sites have not been re-examined and issues re-examined in terms of what we know today as compared to, say, in the 1970s and early 80s when plate tectonics was being developed. So it's a chance to look at older problems with a new eye.
Carol, 40, 50 years out, do you consider now plate tectonics to be a mature field?
That's a tricky issue, and no one wants to.
Right, that's why I ask.
Say, certainly one could argue that mineralogy is a mature field because, we know most of the minerals or that are important and all that, but they're developing new ideas, new ways of looking at it, new questions for especially the environmental patch. I think that for plate tectonics, in most places around the world, we sort of understand to first order what's happened. I think that there are still a lot of interesting questions. I don't think we really understand a lot of issues about the details of how it works. But it certainly is a more mature field than 30, 40 years ago, in the sense that we have answered a lot of questions.
One way to get at the question of maturity is, what do you consider now settled science? What is no longer being debated that might have been a big question in the 70s?
I think the biggest issue is plate boundaries, I think, and the motion of plates. In the 70s, all we could really do was determine 3 million year averages from the magnetic anomalies on the seafloor and earthquakes and direct motion directions and transform faults. And we could only really outline the big plates, and which there were maybe about 14, something like that. Now we're probably somewhere on about 100. And we didn't really understand the difference between what was going on a plate boundary that we thought was a really narrow 100-kilometer feature. And I think that with GPS today and overall better understanding of how deformation strain is distributed when we have plates, for example, colliding, that we're starting to separate out this issue of interplate, that is what's happening really within the plate boundary zone, and intraplate, that things we thought were intraplate because they were in the middle of a big plate, we now with GPS especially can start sorting out what's really a motion of a smaller area that's acting like a rigid plate. So I think that's the biggest thing.
Carol, to flip the question around, what are some of the biggest ongoing debates in the field, despite all of the advances over the past 40, 50 years that remain?
I think the biggest issue really is how the plates move.
Mm-hmm.
At least to me is kind of what really is going on, coupling or the interaction between the rigid plate and the, for lack of a better word, asthenosphere or the more fluid-like material below. And of course, how to understand when the Earth finally fails and you get the earthquake. I think that we've made huge progress. It doesn't help the average person, but we've made huge progress with understanding why earthquakes occur where they do, which was a big mystery, certainly before plate tectonics. But I think one of the big issues is just trying to figure out when the Earth will move and for better forecasting. And there, I don't think we've made much progress other than we know there have been earthquakes before. I mean, we've made a lot of progress with the paleoseismic record of kind of when these earthquakes have occurred in the past, but it's clearly a very irregular process.
Carol, on the question of helping the average person, do you feel that your research contributes to that broader debate about whether earthquakes can even be predicted? In other words, not it being a limitation of our science, but even understanding if the Earth itself knows when an earthquake is going to happen?
Those are good questions. No, unfortunately, I don't think my research has anything to do with that. And we may be debating it 100 years from now.
That's right. Just as a snapshot in time, what are you currently working on?
Currently actually working on passive continental margins that have rifted. And one of the interesting questions is that for about half of them, they're very volcanic rich, that is under all the sediment that's accumulated after the rifting. There's often a very thick accumulation of basalt. And one of the questions is how much has come out before seafloor spreading starts, and how thick it accumulated, how that relates to the kinematics of rifting, perhaps, and volumes of seafloor relative to seafloor spreading that will then start.
Now, when you talk about rifting and margins, I wonder if you can translate those technical terms for me. What are you referring to?
Well, the land that we stand on, continents, move around a lot. And it's not just that we get more frequent flyer miles between us and Europe because of seafloor spreading and new material coming up and pushing and widening the Atlantic Ocean. But that continents sometimes collide with others, like India is colliding with Asia, and then they also rift apart. We see relatively young rifting today, for example, that the Arabian Peninsula is moving away from the rest of the African continent along the Red Sea and the Gulf of Aden. And so probably starting about 30 million years ago, the continent started the Arabian Peninsula started to stretch away from Africa. And as it started to stretch, the continental crust between what's eventually these two fragments got thinner. And eventually, this particular part of the world was successful. And Arabia, actually, the continent, the block of Arabia broke off, rifted apart from Africa. And now we have two passive margins on either side of the Red Sea and the Gulf of Aden. And in most parts, seafloor spreading has actually started.
Carol, maybe it's methodologically or intellectually, how do you separate out your studies of seafloor plate tectonics and land, continental plate tectonics? What are those divisions that are relevant for you? In other words, are they totally separate fields of study, or where are the connections that you see?
I think that a lot of the break really has to do with where you're looking at the data. Mm-hmm. There are loads of geologists who are mainly on land, going out to areas, looking at them. There are marine geophysicists, and that's kind of marine geologists, kind of where I started in my career in grad school, who are actually looking at the data from sea. And often the interface to crawl up and evolve and to go up onto land is a difficult one to branch, because you've got to try to understand how the rocks you see on land relate to the rocks that you see on the ocean seafloor. And hopefully we'll get enough data from both to try to connect the two.
What would it take to get there? What's the best case scenario?
um, I think a lot of it is in the end deep drilling of wells between on land and then on sea and trying to connect up the sediment packages, and also doing seismic reflection data where you send out sound signals, they bounce off, and you would try to map what you see on land to what you see in the margins off underwater. It is a difficult one to try to link up.
Carol, either by accident or on purpose, has any of your research led to applications or translations in a commercial sense?
Not that I'm aware of, unfortunately.
Unfortunately.
It would be nice, but no.
What about computers, Carol? All of the growth in computational power over the decades. How has that changed your research or not?
I use a lot of seismic reflection data for my current project and have used them before. And the computer power now makes it easy to handle a lot of seismic reflection data, seismic data, and to be able to image what we're seeing on the seafloor much better than when we were just recording them acoustically. Mm-hmm. I think the ability to handle large data sets and look at them in, be able to handle them with computers has greatly changed our ability to understand what we're observing. And I think that in general, computational power has gotten much easier. I mean, when I started out, if you wanted a computer, you either bought an expensive little desktop computer that was mainly for drawing little simple diagrams and editing manuscripts, or you went to the big computer center. It's obviously, there's a lot more power in our iPhones or whichever phones we're using than we had back then. For me, my other than the handling of data sets that others have largely put together, I haven't really changed. I have not gone into the computational aspect of our field, but it has changed the way we can look at problems and do much better data analysis.
Carol, a service question as it relates to the main scientific societies you've been involved in. Where is the overlap between the Geological Society of America and the American Geophysical Union?
They both really do the same thing. And cover the same material. When I started out in this field, GSA was considered sort of the old stodgy one and hard to break in, and the one that most people went to, and a place where a lot of the early plate tectonics papers were actually published. And you had to submit your abstract months in advance, and it may or may not be accepted. At least the rumor was there was a 50% acceptance rate. And AG was so much easier. It was a smaller group at the time for the meetings, but it was so much simpler submitting it, and you knew that if you submitted it, you'd be accepted, unless what you did was completely unscientific. But yeah, I mean, for any grad student, you know, that wasn't an issue. And the meetings were small and more intimate. And then the management of AGU tried to get into every field, including what GSA was doing, because back when I started, it was really more geophysics oriented. And, you know, they started getting into everything else, and they've grown, and GSA hasn't kept up. I think right now, GSA does a much better job with what we call boots on the ground, people who are really going out and mapping. And it's been a good place to go when you're looking at an area from a geophysics viewpoint and you really want to integrate that with the geology, what people are observing. But I think both societies actually do more or less the same thing. So I don't think there's really that much of a difference.
Carol, to set the stage, going back to your time at Caltech, when you were in high school, were you specifically interested in geophysics and seismology?
Yeah, sort of. I had sort of a little unusual path in that my older brother had already gotten interested in geophysics and was at college. And so, yeah, being the little sister and 6 grades back, it was kind of a natural thing to be interested in and read about and want to follow in the footsteps.
And were you attracted to Caltech because you were aware of their reputation with the Seismo Lab?
Actually, although of course I knew about the Seismo Lab, that really wasn't my interest when I went there. I was really interested in astronomy and wanted to go in that direction. And when I got to Caltech, I realized that at that time, astronomy seemed to be largely, you could succeed and get interested in it if you could build a better widget for the telescope. And that wasn't my strength. And I also, as a Caltech freshman, you had to take a certain number of so-called lab courses as part of your distribution. And one of them that I took was GE1 with Hiro Kanamori, who's a seismologist. And so that's kind of how I ended up switching my interest to geophysics.
Carol, you entered Caltech, was it 1974?
Yes.
Now, what was the class that Hiro was teaching? Do you remember?
GE or Geology 1.
So this is like just intro to the field.
Yeah, well, there were a number of different faculty who taught it. And that has taught GE1 over the years. And like a lot of these courses, what you taught really boiled down to what you were interested in. So if you had a geologist, they would be more geology oriented, the geochemist more and it was sort of an introduction to geophysics course, actually. And I really liked it. It was a lot of fun.
Do you remember what Hiro was working on at that point? Or more broadly, as an undergraduate, would you have a window into that kind of thing?
Well, I actually worked for about a year doing some data analysis for him, looking at earthquakes and measuring magnitude of earthquakes from seismic records. So that time, I think there was a lot of, in general, using surface waves to try to understand improve earthquake focal mechanisms. That is a fancy word for how the earth actually slipped in an earthquake, looking at it from the seismic waves and trying to figure out whether it was, say, a strike slip earthquake or a thrust or a normal fault. What was the sense of motion in that earthquake?
Carol, as an undergraduate, was your sense that at the Seismo Lab there was opportunity to do real research on your own, or were you mostly, shadowing graduate students, that kind of a thing?
I think that any undergrad who wanted to get involved with research could.
Yeah.
I'm not sure at the time there were many geophysics majors who were doing that much research. And the Seismo Lab was an interesting place because I think everyone except for maybe one faculty member was really earthquake oriented. And only one or two maybe were more what sort of general plate tectonics oriented.
Carol, how many women were in the program as an undergraduate when you were there, roughly speaking? I mean, would you be the only woman in most classes, or was it not that bad?
Well, my first class that I walked into was a history class, and in most colleges they have these little kind of writing classes or smaller seminar type classes, and this was a history class, and the professor looked at me and said my name, and I was the only girl out of 15. It was 10% women for my entering class, so it was. I think that was, yeah. Well, the school had only gone, the undergrad program had only gone co-ed a short time ago, and I was in the 5th class that accepted women. So, but yeah, after a while, you just kind of accepted it. It wasn't a big deal. And in fact, I remember at lunch sometime when some students who had been accepted and were thinking about going to Caltech as undergrads, what we would call pre-frosh, a friend sitting next to me said, well, going to Caltech is sort of like being in a monastery. And it just, that wasn't the way I was thinking, at least. But, there were a few more women in geology. Not that many in geophysics undergrads, but I think there were maybe 3 or 4 other women in some of the beginning geology classes.
What about faculty? Were there any women faculty?
Not in the Seismo lab. I think the only female professor I had was actually in a humanities course. Part of it is that there had been sort of a wave of some women going into science, but maybe starting 10 years before I went into school, but I don't think it had really there were hardly any in earth sciences at the time.
Now, you were in the academic generation after the move from the mansion. Was your sense, from talking to people who had been there longer, that it made the Seismo lab less of an island? In other words, did it become more integrated with GPS and the campus generally as a result of moving into MUD?
I think moving into New MUD made it, a little bit more linked to the rest of the campus. At the time, I really didn't have any feel for how much more connected they were to the rest of the division. But what I really remember is the building just had that new, fresh scent. I don't know how else to say it. Everything was clean. It was big. They had huge offices and lots of room for grad students and even undergrads who wanted to work. They had nice little cubicles for them. And I think the faculty were really enjoying, and the grad students, the new extra space. So it was kind of like, wow.
Carol, what were the big debates at the time? What were people really excited about?
I don't really have that much of a sense. I think that the big excitement was really with the change from in the technology to take the seismic reflection waves from a seismograph and to be able then to understand the motion in the earthquake. I think that this was a big excitement because they could look at a lot of areas and try to understand a lot of areas much better than they had in the past. So that was my biggest sense, that a lot of it was just trying to understand with this new technology, even basic issues like when you had a certain size of an earthquake, how much slip did you have on the fault, how much motion. So a lot of new things that you could do by looking at the moment of the earthquake, trying to understand how long the fault slip had actually moved. The shaking from an earthquake, the really big ones can go on for 2 or 3 minutes even in an area because of the way the waves travel. But how fast did the fault actually move, as opposed to sort of the ringing later on of the earth?
Did you benefit from visiting scholars? Would people come to the lab from elsewhere to present research, interact with the faculty there? Was that part of your experience?
I never actually interacted much with visiting scholars, a little bit, but not much. But what was really nice is that undergrads were encouraged to go to seminars. I remember as a freshman who had just decided to change into geophysics that being very puzzled by these terms like Cretaceous and Jurassic, long before Jurassic Park. So, and sort of a lot of these basic terms. But it was really fun to be able to feel that you could just come in and go to seminars and hear what people were doing and saying.
Was your sense that the Seismo lab had proprietary instrumentation, or at least instruments that no one else had at that time?
That wasn't on my radar. They obviously had their own instruments, but that wasn't, and their own network for Southern California, but that wasn't something that I was involved with. I was very aware that when you had a big earthquake, they were always on TV, or being called up. But that was not something that really, as an undergrad, was something that I wondered about or worried about.
What about the proprietary nature of data? In other words, today we see that data is democratic, it's worldwide, it doesn't really matter where you are as long as you can gain access. Was the Seismo lab at that point an archive of data that simply wasn't available elsewhere?
I think that some of the data that I worked with, it was available elsewhere, but you had to know how to get it, at least, and whether or not someone, this is speaking as an older scientist, whether or not someone would know how to go about asking, I don't know.
Now, did you stay on campus during the summers? Was that an opportunity for you to do more research?
I did a little bit of research over the summer, yes.
And what faculty did you work with? Who were mentors over your undergraduate experience?
Hiro Kanamori, who was my undergrad advisor.
And what was his style as an advisor? Would he give you problems to work on? Would he let you go explore on your own? How did that work out?
It was mainly that I was doing some data gathering for him, measuring some material. I wasn't actually involved with a paper itself. It was just making some measurements that would then be useful ultimately for what he was doing.
Which was what? What were the big questions he was after?
I think that his question that he was after at the time was simply the relationship of the different magnitude, way to measure earthquake size. Initially, when people were looking at the size of earthquakes, they used a magnitude scale that was based on a seismometer that was very sensitive to relatively short periods of the earth motion. And as they had seismometers that could also look at longer wavelengths for the earth, that it was realized that as you got to the really big earthquakes, that what we would call the body wave, and one variant of that was the Richter scale, wasn't as good representing the amount of energy as the surface waves that traveled mainly on the upper surface of the Earth, maybe the most 500 kilometers, and didn't go down that, and had longer wavelengths. And the really big ones earthquakes had more energy in this area and would be a better representation of the amount of energy released. And so I think a lot of the interest that was kind of which scale to use. And then in addition to the shorter wavelength first motion or energy that would come in, or the later surface waves, Hirakanamori, and this was not what I was involved with, was one of those working on something that's now, I think, I'm blanking, but a moment magnitude based on trying to estimate the whole amount of energy, which is related to the amount of motion on the fault during the earthquake, whether it's like a centimeter or 10 meters, and then the surface area of the fault that's moved. So these were some of the big questions of how you should represent the amount of energy, because then you could start looking at the significance of the earthquakes and try to separate out, it sounds silly, but the magnitude 7s from the magnitude 8s and the 6s, and gives you a much better idea of what's going on seismically with an area.
Was your sense that Hiru was representing a particular school of thought, and was there an opposing school of thought at that point?
That was not on my radar.
Above your pay grade.
No, it's not even that. It's just that as an undergrad, you're still taking most of the basic courses.
Sure.
And at least among the faculty that I had classes with, I never detected any difference of opinion, for lack of a better word.
Do you have a specific memory or like an aha moment when you realized you were good at this, you liked it, and this is something that you might want to pursue professionally? Did that happen at a particular juncture for you?
Nah, there wasn't any bright, shining flash or anything like that. It was kind of gradual.
Well, when did you start to think seriously about graduate programs?
It sounds kind of silly, but science was expanding and departments were expanding, and geophysics and plate tectonics was the big thing, and all the various aspects of studying it. And well, of course, people, when there was the possibility of going to oil companies or similar things, it never really occurred to me. I just kind of decided that the faculty path was a grad school path was one that I was going to take. So there wasn't any great angst about it. It was just, I assumed that's what I would do.
What kind of advice did you receive about programs to apply to, and specifically whether or not to stay at Caltech for graduate school?
I don't think I wanted to stay at Caltech. I mean, it was a great place, but I think I felt that I wanted to get a more variety. And at the time, you spoke to some of the grad students and other people, and just kind of decided where it might be worthwhile to apply. So I think a lot of grad students, even today, you ask a few people and you decide, you don't necessarily do a great search on it. And at the time, since everything had really been oriented towards seismology, that's what I was interested in. I didn't stay in seismology in grad school, but that's what my focus was for looking around at places. And
then ultimately, why Columbia? What was attractive about Columbia?
I think of the places that I looked at, I just liked the friendly environment, and it seemed to have a lot to offer and a lot of different things.
So going in, what was the game plan? What did you think you were going to be focusing on?
I thought I'd be a seismologist. And I got there, and I like the people there in the seismology group. That's not the issue, but I wasn't interested in the end of either, and I realized it wasn't my strength, working on really theoretical seismology, or they had a big program also in using their network data to look at aspects of problems. And they had so many other people doing so many other things with aspects of plate tectonics that I really became intrigued with marine geophysics, and ended up switching to heat flow, marine heat flow.
And was it Lamont Doherty? Is that where you were originally?
Yeah, it was then Lamont Doherty Geologic Observatory, but I moved up the hill from the seismology department to the marine geology and geophysics division.
And what was the point of entree? Was it a professor? Was it a class? What caused you to switch?
I really don't remember. It was too long ago. But I think the big thing was that at Caltech, it was almost all exclusively seismology.
Mm-hmm.
And looking at how much else, all other tools you could use to understand plate tectonics was a real eye-opener.
And for people that don't understand these nuances, where it all sounds like it's the same field, how big of a transition was that for you?
It didn't seem like much of a transition.
It was only a different building, essentially.
Well, it was different problems that we were looking at, but it was, all the same of trying to understand how the surface of the Earth was moving around. And it was just a different tool to understand, and different data to understand the Earth.
Who ended up being your advisor?
The main one was Roger Anderson.
And what was Anderson known for?
He had also started off in heat flow, marine heat flow. And by the end of my grad student period, he had actually gotten involved with the ocean drilling program and was building up a lab, a group to send in to better understand for this program's drilling, to go down to understand the characteristics of what were in the hole, and kind of a more of a oil company approach to understand the permeability, how easily fluid went through it, and other characteristics.
What was your thesis research on? What did you ultimately focus on?
I went out to the central Indian Ocean, kind of 1,000 kilometers south of India, and I was looking at an area that at the time was considered an interplate, that is, within a plate deformation zone, where the oceanic crust had been deformed in these great folds, which we now know is actually a very diffuse plate boundary between India and Australia, and that was half of it. And the other half was looking at a little area off of Arabia, where we were trying to figure out whether we were dealing with oceanic crust or thin continental crust, and how the Gulf of Aden extensional spreading had extended out into the Indian Ocean.
And what was the vessel? What was it like conducting this research?
We ended up going on a ship called the Vima. I don't know if you've ever heard of Vima.
No.
Okay. The big thing for oceanic institutions and plate tectonics at the time was getting a vessel to go out and to do mainly two things, although they were gathering other stuff. One was to tow a magnetometer on the seafloor and see the magnetic anomalies, so they could then, from the Earth's reversal history, figure out how old the oceanic crust was and how fast the oceans were spreading. And the other was to gather data about the seafloor and a little bit below with seismic techniques to try to understand what went on. And in addition, they would take a core, mainly going down maybe 5 meters at most, to understand the sediment and the sedimentary history. And from that, you could get some other interesting aspects. There was also measuring gravity, too. And in order to be in the game, you needed a sailing ship. So the Vima actually started out as this sort of luxury sailing yacht that the folks at Lamont purchased and put on an engine and put the equipment on. And it was sort of getting up in years. I guess that's the kindest way I could say, although a huge amount of science had been done. So I was actually on the fourth and the third last science legs, about a month long, of the Vima. And the equipment was relatively old compared to other institutions and their ships. And before I went on the Vima, I took a month science cruise on another ship with I was just helping out with folks doing heat flow. And I remember they were looking at all the new equipment and just in amazement. But it was a lot of fun, and got a lot of good data and answered some questions, but not others.
And why a sailing ship? Why does it have to be a sailing ship?
It didn't. It was just that was the ship that they could get that was big enough that they could then convert with an engine. And they did things, especially when they got it a long time ago, relatively cheaply, and that was available, and that's what they thought they should use. And of course, the sails were gone by the time I was there.
And what was this NSF supported?
Yes.
And what's the history of NSF supporting this subfield? Does it go back a long time?
I think, that's something you have to ask someone else, but I think certainly after World War II, there was a realization that they needed to know more about the seafloor. And with the development of the idea of plate tectonics, the only way to get the data to better understand what was going on was to go out and make measurements.
What were some of the conclusions of your thesis?
One was that, at least in some places, there was somewhat higher heat flow. One was that the earthquakes were showing us compression in the area, and the folds everything was still actively deforming. And it was certainly deforming the upper part of the Earth's surface. The other thing that we did was we went out and we took sediment cores. There were other sediment cores that were there before. And we asked others, this was not our specialty, but at Lamont, to date this oldest sediment that they could find. And it indicated that the deformation had been going on for about 8 million years. And so that was something that was really useful too.
And what were some of the bigger debates in the field at that point, and how might your thesis research have contributed to them?
I think that there was an overall debate as to how these folds, what was causing the interplate deformation. What was going on with the crust. I don't think it really solved anything, but we did show just how widespread these folds were over the huge length of area. And at some level, how the directions changed of the fold. And later on, that those directions were used when people, others, to look at the forces involved in the plates, and to realize that the shape of the fold, the orientation of the folding, and where it was located was in fact what one would expect, with a lot of stress building up within the larger area due to the plate motions, due to the seafloor spreading, pushing stuff to the north in the Indian Ocean, and the compression from India colliding with Asia.
Carol, after you defended, what opportunities were available to you?
I was already involved with another earth scientist, and we had gotten married. And I was very fortunate that there was a postdoc where my husband was working. And also at the time in 1984, this was in this period of time where a lot of universities were hiring geophysics people and really building up that aspect, the way colleges now are building up and getting more environmental people. And I was just very lucky that relative to where I lived, there were 2 faculty jobs that became available in geophysics in the fall after I got there. And I applied for both, got offered both, but chose the one that was closest to my house. So so we don't have to go to the same faculty meetings. And
it's a great way to resolve the 2-body problem.
Absolutely. We were very pleased.
Carol, did you take on new research as a result of your faculty appointment, or were you looking to continue what you had done previously?
I think that I carried over some of the work that I'd been doing as a postdoc, and I largely continued using heat flow measurements that had been already made and were available in the database to understanding other problems. So initially, it was working largely in the same area. I did expand areas that I was using heat flow to try to understand what was going on. One of the big areas that I expanded into, and I don't know if you've heard of this, it's not trendy anymore, but something called the South Pacific Super Swell. There's an area around Tahiti, and there are lots of little islands there that has a lot of volcanism and what we would call hotspot tracks like Hawaii. And one of the big debates about 5 years or so after I graduated was what was really causing this area. Whether it was, at the time, there were sort of 2 competing ideas about how, when you had a hot spot like Hawaii, kind of what was going on beneath the crust, beneath it. And one of the ideas was that the area around, say, Hawaii, or these other features, like Iceland, for example, was elevated because most of the area down to maybe about 100 kilometers so had much higher temperatures. And the other was that most of the uplift was due to what we call dynamic forces of the mantle kind of pushing up and raising the area up. And the problem was that when you looked at the elevation from like Hawaii and the others where the hot spot had passed, that the subsidence of these island chains could be viewed as either a thermal process like cooling as the oceanic lithosphere moves away from the ridge crest and everything cools, or kind of, this push up, and as it moves, dynamic push up of the forces, and as it moves away, everything kind of cools down. And so I had attended a seminar about this, in fact, at AGU, and the area was supposed to have been really reheated, and the oceanic lithosphere, kind of the strong oceanic plate, thinned and heated. And I kind of came away from that saying, oh, well, no one's looked at the heat flow data for that area. Is it really hotter? And so I pulled out the data with a colleague, and we concluded that it wasn't any hotter than similar age elsewhere. And not only similar age elsewhere, but also, I should back up. I should say, the first thing people mainly did was that they would say, okay, how does this compare to what was considered the theoretical cooling curve at the time, and the best reference curve for how heat flow should vary with age? And so we did that, and it looked sort of okay. And then someone said, well, and I don't remember who, but said, okay, that's all great, but you got to look at what the same age crust is elsewhere to see how your data for this area compared to everything else. So we were doing that too. And what we concluded was that not only wasn't the heat flow unusual for this super swell area, but also in order to explain how the load from these volcanic islands had bent this surface, that we would have needed much higher temperatures, and we should have seen super high heat flow if it was a thermal process. So it obviously wasn't a thermal process that was producing this anomalous area. I mean, yeah, volcanism is hot, but what's it doing to the rest of the stuff beneath the plate? And that kind of process ultimately led me into looking at the global heat flow data with age and asking the question, how well did the current reference curve for how heat flow should and depths of a seafloor should vary with age, how well was that curve doing?
Carol, you mentioned Iceland. When did you start to get interested in Iceland?
I think that was really after I had done a lot of work on other hot spots, mainly in the Pacific and Indian Ocean. And so it was much later.
And what's unique about Iceland? Are there things that happen there that the rules simply don't apply elsewhere?
There are very few places today where the mid-ocean ridge comes up and the seafloor spreading to the surface. And one of the fascinating things about Iceland has been that others have put GPS stations on Iceland, which you can easily do on land, and seeing the spreading rate, that the spreading rate on Iceland is the same as what the magnetic anomalies are telling you in the ocean seafloor surrounding it. The magnetic reversals with time that we can see in the seafloor, we can see in Iceland. So it's a really neat, fascinating place, besides just a great place to visit.
Carol, more broadly, what have been some of the big takeaways for you in the thermal evolution of the seafloor? What do we know now that we didn't when you started in this work?
I think the bigger thing, a lot of it is the oceanic seafloor at older ages, mainly about 80 million years to the oldest stuff. That I think that when I started out, the assumption was that old seafloor of that age have been so affected by hot spots, by thermal anomalies coming up and volcanism, that it wasn't really that useful to study, and that a lot of the when you're at younger ages, you've got a very rapid decrease in elevation, and it does sort of slow as you get to older stuff. But the assumption was that most of the old seafloor was hotter and shallower because of the hot spots. And I think a lot of the work that I did showed that a lot of that was that it wasn't hotter and shallower because of hot spots, but rather we used the wrong reference model. And that with a better reference model, and others are improving since what we've done, but that you can explain the average thermal heat flow and depths of old oceanic seafloor with the same model that you can explain the younger stuff. I think a lot of it was really, in some ways, a data issue, because when the first reference model that people were using was done, it was a lot harder to get data from everyone, and the maps weren't as good, and because they thought that so much was affected by the hotspots, they only mostly use depths for the old seafloor based on areas that were really deep, because they thought they were avoiding the constructional features. And so they really biased their model at a time when we didn't have much data from old seafloor, because a lot of the old seafloor, the ages weren't known. They really biased it to deeper areas, and we were in this position then that 90% of the seafloor had depths, of old stuff had depths and heat flow that were way too shallow and high heat flow compared to what this reference model was telling us. And so I think with more data, it became obvious that it was a slight reference model issue rather than a hotspot issue.
Carol, your work on hydrothermal circulation, is that separate from the broader effort in thermal evolution, or is that part of that study?
It's part of it, because if you're, my issue and the thing I was interested in was how much heat has been removed from the ocean seafloor. And to be able to answer that, you first have to have confidence in your reference model. So the amount of fluid flow, which then others can use to try to understand what's going on, you need to have a reference model that works. And so it's sort of connected in many ways.
Carol, I'm curious if your work on the mid-continental rift ever inspired broader thinking about just how that influenced history, human history.
I think that humans have well, I'm not an anthropologist, but they've only been in North America, as far as anyone knows, for about the last, certainly maybe 20,000 years at most, probably a little bit less. So they weren't around 1.1 billion years when the mid-continent rift formed. It's not like the East African rift that's currently extending in Africa, where there's a lot of work that tries to show how that feature really influenced human evolution. But I think that the mid-continent rift is only exposed in a relatively small area, in the shores of Lake Superior and going a little bit towards Minnesota. And it's certainly true that the copper that both can be mined, and Native Americans did mine it actually, and also with the glaciers moving over the area, carried the copper fairly far south. So that certainly had an impact on how Native Americans would have had some copper that I guess was certainly used for decorations. The other thing is that the shape of Lake Superior has, of course, been controlled by the mid-continent rift structure, and certainly was an important area, I'm sure, for fishing for them even, and transportation. Although I think a lot of them tried to avoid going out in the middle of it. But so, I mean, it certainly had, I'm sure, a development relative to the tribes and their resources.
Carol, I asked about the uniqueness of Iceland. What about Costa Rica? What have you learned from the Tico Flux Research Project?
There was a really interesting heat flow discrepancy where the crust was more or less the same age, and one area had super low heat flow and the other had super high heat flow. And these were all made with relatively old equipment. But the first folks who went out and made marine heat flow really knew what they were doing and got good data, even though it was old equipment and only a few heat flow, only a few temperature measurements. And when we got out there, what we found was that there was this incredibly sharp divide between the area that had incredibly low heat flow for its age and the area that had essentially normal heat flow for its age. And a lot of that was because of the seafloor irregularities from its formation, that the really cold area had a lot of seamounts, and seamounts that were exposed to the surface so fluid flow could get out of it. And the area that was really warm had essentially no exposures of the seafloor and sediments all the way on top. So that this really was not a tectonic issue, but it was an issue of what was controlling the water flow. And what was fun is that when people realized this difference between the two, and this oceanic seafloor is subducting beneath Central America, that they realized that the depth of earthquakes where it started was different, and there were differences relative to the hot stuff going in versus the cold stuff going in. So it was a really fun project. I think also that not what I was involved with, but we collected a lot of water samples from the areas where there were seamounts, and just understanding that even in 25 odd million year crust, you could have fairly vigorous circulation affecting the ocean chemistry of the water going in, exchanging between the rocks and coming out, and even some little seamounts that are, I think they later found even some community down there, although I don't know the details about that.
Carol, on the teaching and mentorship side, for your department, is there a large graduate program, or are you primarily focused on teaching undergraduates?
No, we've got a program that has had between about 15 to 20 odd graduate students each year. Although we obviously teach a lot more undergrads than that. And when I started out, it was mainly, the graduate program was mainly masters. And if you're at a state institution, I'm not sure how it works at a private one, but at a state institution in Illinois, you can't just declare this is our PhD program, or this is this, or this is that. You have to go through the correct boards of education to get approved. And at the time when UIC started in the 60s, we had a small department. Unfortunately, we still do, but we eventually got a PhD program by working with the civil engineers, and there wasn't that much interaction in the end between the two, but we could put our grad students through it. And it wasn't until maybe, I don't know, maybe 10 or 15 years after I got there that we finally got our own PhD program. But and now we have more PhD students than masters. Most of the teaching everyone does is at the undergrad level, and it's a really diverse population. Many of the students are the first generation of their family to go to school, and it's a real challenge teaching them, because even though now we have, not in a bad way, but they have real challenges because most of them are living at home and they're trying to balance family issues and issues working to be able to afford to be in school and schoolwork. So it's, but for a lot of them, at least initially when I was teaching, that they spent so much time on these other issues that they'd never, I wouldn't, when I say get out in the field, they hadn't even gone to a lot of the forest preserves that are part of Chicago. And so it was a lot of fun really expanding their horizons about volcanoes and earthquakes and even the little field trips that we would do locally. So,
Carol, bringing our conversation back to Caltech and the Seismo lab, have you kept up with the lab over the years? Is there an alumni association or anything like that?
Not, as far as I know, not for the Seismo lab, and no, I haven't kept up. I still have my cup, which is at work, not here, but for the Seismo lab cup, and use it. But no, I haven't kept up with them, no.
Carol, for the last part of our talk, a few retrospective questions, and then we'll end looking to the future. I wonder if you can reflect on the opportunities that you receive simply as being part of the Seismo lab, in terms of connections, in terms of a way of approaching problems. What were you able to achieve, do you think, as a result of being there for your undergraduate program?
I think the biggest thing was the openness of people around me, faculty and grad students, just to treat an undergrad as equal. Answer questions, see their excitement about science. So it was, and of course, even now that in most places, geology number of majors are relatively small. So you have a connection to your advisor, to not only your advisor, but your instructors that you don't have elsewhere, where you're still taking classes with hundreds of other people. So it's just kind of openness, ease of communication, and all questions really being considered respectfully.
Carol, the counterfactual question: had you stayed at the Seismo lab for graduate school, do you think your field of research would have changed much differently than what it actually was?
I don't think I ever would have gotten involved with marine geophysics. I think I'd still be doing seismology.
And to go back to those big questions about debates and unanswered questions, where are you most confident that the things that are currently still not understood, what's the lowest hanging fruit? In other words, what's the frontier for which there's real possibility for the next coming generation of seismologists and geophysicists?
I'm not sure I know how to answer that question relative to what you're asking. I think that there's to me, at least for relative to what I do now, I think that we still really don't understand a lot about how the central U.S. formed. We say that there are a series of collisions that have built up. I'm talking about long before Pangea. I'm talking about in the Precambrian time, before 500 million years ago, that there have been a whole bunch of collisions that built up the kind of central part of the U.S. I don't think we really know very much about it. I don't think we know the weaknesses. I don't think we know very much about, under maybe a kilometer or so of sediment, what are the potential resources if it is cost effective to drill down, not oil, but minerals and stuff to get. And I think that until money is forthcoming to really do a lot of really high quality seismic reflection experiments and drilling through the center of our country, we're still not going to know really how it formed over time.
And finally, Carol, last question for you, looking to the future. What are the most important research projects you haven't yet taken up?
There are loads, but I'm too close to retirement. I'll leave them to the next generation.
Well, I won't let you get off that easily. What should the next generation focus on, if not for you?
I think that it's really too hard to tell. I mean, I think that they're going to have to define the problems, at least from my perspective of the hole that I was sitting in when I started grad school. Continents just kind of split apart, and that was it, and no one really thought too much about how you got from the continent to seafloor spreading. It was just kind of like, there's this continent ocean transition zone, and we'll leave it at that. And over the years, work has really shown how complicated it is. And from my grad school perspective, I don't think, in knowing what we know now about the different ways it can be stretched, how it's stretched, how it subsides, I don't think from starting at the Seismo lab and starting college, I would have thought about that. And so I think that there will be new problems and challenges, and a lot won't be what we anticipate today.
That's always a safe bet in science. Carol, it's been a great pleasure spending this time with you. I'm so glad we were able to do this. I'd like to thank you so much.
Thank you. Enjoy.